Hello everyone, this is another lecture, and this one we're going to talk about continuous probability distributions. Okay, in the previous lectures we talked about probability in general, random variables, discrete random variable distributions, and now we're going to talk about continuous probability distributions. Okay, so just to remind you of what we mean by continuous. So when we discussed random variables, I mentioned that random variables can be either discrete or continuous. Discrete means that the value of the random variable can take finite number of values, right? It doesn't matter if it's integer or if it's decimal, right? So it could be 1, 2, 3, 4, 5, it could be 1.5, 1.6, 1.7, but it's still discrete because we have finite number of them, finite values that x can take, right? While in continuous, the numbers, the value of the random variable can be infinite, right? So, for example, if I have x as a continuous random variable that ranges from 0 to 10, take a value from 0 to 10, right? If I divide this into two halves, there is still infinite number of values that x can take from 0 to 5. I can still divide this further and further and further, and every time there is infinite number of values that x can take from these two points, any 2 points, right? So the implication of this is that the first implication is the value of a single, or the probability of a single variable, a single value, is 0, right? What I mean by that is, here's the probabilities again. So it can take, the probability can take any value. X can take any value from 0 to 10, as I said before. The probability will take range of values as well. If I try to find exactly what is the probability of x here equal 4.5632 as an example, this one is still 0. Why? Because the probability here is so small that it's always close to 0, right? So when I deal with continuous probabilities, I always deal with ranges. I cannot deal with a single value. That's the first implication, right? So here we will see that a cumulative distribution function is the same as before, is the same as the discrete case. It represents the value or the probability when x is less than or equal x. Okay. But since the value of x itself is the probability of x, a single value, is 0, so there is no difference between these two expressions. These two will be the same. X less than or equal x, small x, or x smaller than small x, they are the same. Why they are the same? Because the value, the probability of x equals 0, or x equal, let's say, a specific value, is 0. So these two are the same. And the cumulative distribution function for them is the same. So when we are looking for continuous distributions, the x or the sign less than or equal, it's the same as the sign less than. And the same thing for greater than or equal will be equivalent to greater than for probability for the cumulative distribution function. And that also gives us more results when we talk about the total or the range of probabilities from x equal or greater than a to b. When we talked about discrete values, we calculated the sum, right? We did the sum of values. So if I want to find the probability of x from 1 to 4, it's the equal of the sum of probability of 1 plus probability of 2 plus probability 3 plus probability of 4, right? When we talk about continuous, it's an integration. It's integration of the area below the curve. So if A is somewhere here and B somewhere here, we are the probability of x greater than A and less than B is the area under the curve, which means we use integration from A to B of the probability function. And this is equivalent to taking the CDF of B and CDF of A and subtracting them, right? Because when you compare the two, the area here, the red, this is FB, and if I take the blue here, that's FA. So by subtracting them, I get the green area. All right. So in general, we're going to deal with continuous distribution the same way as we did with the discrete. It just now, instead of sum, becomes integration. And instead of, and the reverse, of course, if I want, I have to do differentiation to get, let's say I want the probability continuous function from the CDF, I will do differentiation. Okay, so sometimes the probability distribution function itself, or PDF in this case, we're going to call it, we called it mass function before in the case of the discrete, now we're going to call it PDF. So the PDF can be given to us as a formula like the f of x here. F of x is k over x cubed for x greater than or equal 1, and for everything else will be 0. So that will be our PDF. Same as with the discrete, it has to add up to 1. So if I integrate f of x, I end up with 1. So a lot of exercises in this chapter rely on this fact. In the example in page 29 here at the end, it says that the f of x is k over x cubed for x greater than 1. K itself is a constant unknown, but I can find out what it is by knowing that when I integrate the f of x, I'll get 1. So you'll see here in this example, we integrated from 1 to infinity because x can be greater than or equal 1. So if I integrate from 1 to infinity, I will be able to find out what k is, and we end up with k equal 2. And from that we can find out the CDF. And once I find the CDF, if I find it in a closed form, which means that it's easy to solve here, I can find any probability I want, right? So for probability x greater than or equal greater than 1 or greater than 5, it's 1 minus f of 5, and then I'll substitute 5 or x with 5, and I get the result. So generally speaking, there is similar rules for discrete and continuous probabilities, but the definition is slightly different. The PMF here is given as the probability of x equals 0 for x equal small x for different values of small x, right? 1, 2, 3, 4, these are finite. For the continuous, f of x is my probability, right, the function, and it's the differentiation of capital F of x, which is the CDF. And if I sum all the discrete values, I'll get 1. If I do integration, I get 1 as well. So for the discrete, I'll just sum all the probabilities of the discrete values. For the continuous, I will do integration, and so on forth, right? So the comparison here, just replace the sum with the integration. For the joint and marginal densities, same concept as well, right? But I will do double integration or double differentiation if I want the marginal densities, and it's less important in the case of continuous, so we won't be focusing on it that much. Rules, independence, same thing. We have in the discrete case, if x and y are independent, then the probability of x comma y is the multiplication of the probabilities, marginal probabilities of each one of them. For the continuous case, it's the same thing, multiplying both probabilities. Expectations, we talked about expectations before, and we said that the expectation is, for the discrete case, is the sum of x multiplied by the probability of x for all x. If we translate that into the continuous case, it's going to be the integration. So E of x, or the expectation, is integrating x multiplied by f of x for all values. And that applies to the variance as well, so it's the same situation. All right, so most of this is a repetition of the discrete case. It's just now we have to be aware that we are going to use integration. So we're going to get directly into the families of continuous distributions. So these are known distributions that are used quite often for many applications. So we're going to talk about these. The first one is the uniform distribution. So the uniform distribution, the assumption here is the value of the random variable ranges between any two values, a and b, right? Any two values, There is no restriction. They don't have to be integer, they don't have to be positive, any two values between A and B, right? So if I understand that correctly, so anything, the value, let's say the random variable here takes a value from A to B, and we know that the probability is somewhere here, right? And it has to be equal for all values, right? So that's the uniform where every probability between A and B is the same. So it has a constant probability. And we also know that if I integrate the value, the area under the curve here, so the integration of f of x dx from A to B, it will give me 1. So that's the area, right? Integration like this, it's the area. So what is the area here? So um, so this means that if I take the whole area, this is 1, and you know that the area is um, the width multiplied by the height. So the only way the width multiplied by the height is 1 is if the this is the width minus the height. If I multiply by 1 over b minus a, will give me 1, right? So that means that all the probabilities between a and b is they have the same probability 1 over b minus a, right? So that's the meaning of this function here. F of x is 1 over b minus a for all values between a and b. And if I find the expectation, it will be a plus b divided by 2, which is also intuitive, right? So it's the average. So that's intuitive result. The variance is b minus a squared divided by 12. This is very common distribution, and in fact, it's the distribution that the computer can generate very easily. And it generates pseudo-random. So the uniform distribution, one of the basic applications of the uniform distribution is to generate other distributions. And if you go to the appendix of the notes, you will see an algorithm to generate uniform distribution random variables. Okay. So let's take an example here. We'll see if a flight scheduled to arrive at 5 p.m. actually arrives at a uniformly distributed time between 4:50 and 5:10, then it's equally likely to arrive before 5 p.m. and after 5 p.m., equally likely before 4:55 and after 5:05, etc. So what does that mean? It means that if I look at the probabilities here, since all probabilities are equal, if I ask you what is the probability that let's take an example, numerical example here, just to make things easier. So let's say A is 1 and B is 3. And if I ask you what is the probability that the random variable falls between 2 and 3? Well, here the example says that the probability that the number is greater than 2 and between 2 and 3 is the same as probability between 1, and 2 is the same probability. If I further divide this and say, what is the probability that the value is between 2.5 to 3 and the value between 2.5 and 2. So again, the probability here is the same as probability here. And you see here that if I divide the number further and further and further, every time I'll get the same probability, as long as the, obviously the probability from 1 to 2 is twice as the probability from 2 to 2.5. Right? So think of it as the area. This area is twice much as this area, so the probability is double. But these two areas here are the same, so the probability are the same. Okay, so that's one property of the uniform. What are other properties? Often, because A and B are, can be anything, so we need to deal with something that we know the range, we control the range. So we need, because it's easier just to deal with numbers that have maybe from 0 to 1, right? Instead of A can take any value and B can take any value. So if we convert the uniform distribution to something that ranges from 0 to 1, we call that the standard uniform distribution. So the standard uniform distribution is always the value of the random variable ranges from 0 to 1. We can convert between the two, between the regular uniform and the standard uniform, by calculating, by saying that's y, which is the standard, equal x, which is the regular, minus a divided by b minus a, right? So the range, if it's from a to b, we can convert it easily from 0 to 1 by just subtracting whatever x here, subtracting a and dividing by b minus a. So again, the example 1 to 3, I want to standardize it. So I say y equal x minus 1 divided by 3 minus 1, which is 2, right? So if x originally is 1, now obviously become 0. And if b was, or x originally was b, which is 3, now it becomes 1. So y equal x minus 1 divided by 2, which is 3 minus 1 divided by 2, which is 1, right? So I can convert anything to uniform. If I want to convert things back to the regular, I can just flip this formula and give it return or get back our original x. So here y multiplied by b minus a equal x minus a, and then I can rearrange the variables by doing b minus a y plus a. So why do I do this, right? So remember when we talked last time about tables, and if I'm looking for tables or using calculators or using a program of some kind, well, it's easier just to deal with all the variables are from 0 to 1, and then that will accommodate everything, right? So I need to convert, or I need to use these so that I can use general table or general algorithms or general functions in a calculator instead of dealing with something that's, variable from A to B. So we need sometimes to convert between these two. Okay, you see here there's a Python code that you can use to convert or to find the uniform distribution. And we can see some other exercises later. But let's move now to the exponential distribution. So exponential distribution is, again, one of the many, many common distributions out there that we use for many applications. And one of the applications for the exponential distribution is finding out the time between two events. Remember, we had something like this before when we talked about Poisson. With Poisson distribution, we can find the probability of having X rare events in a period of time. Right? This one is giving us the time between the events. So the random variable here is the time between events. So what is the time between two packets arriving at a router? So we can model that using exponential distribution. So the exponential distribution has a nice formula. F of x equal lambda multiplied by the e to the power minus lambda x, where x here is the time, right? Lambda is considered the frequency measured in 1 over t, right? So let's say if I want to find out again the time between two packets, I have to say, well, the frequency of arriving at a router is given by 1 over 3 seconds. That's the frequency. So I'm going to give you the frequency of arrival, and I ask you, what is the probability that the time between two packets is greater than 5 seconds? So this is the kind of applications for exponential distribution. Now, lambda, if I take the inverse 1 over lambda, I will get time, right? So if lambda is frequency, 1 over lambda is time, and that will be our mean or our expectation. The variance is 1 over lambda square. And if you integrate f of x, you will get a capital F of x, which is the CDF. And the CDF is also looks nice. I can calculate it. Don't forget the 1 minus. That's f of x, right? Has 1 minus e to the power minus lambda x. The time is always positive, right? So x is defined above 0. So there is no concept of minus time here. So x is always positive. Okay, so in this example, if print jobs are sent to a printer at an average rate of 3 jobs per hour, so here rate is another term for a frequency. Average rate is 3 jobs per hour. So another hint, per hour. So another hint that we're talking about rate here or frequency. So 3 jobs per hour. What is the expected time between jobs? So here we can apply this formula directly. The expected time is 1 over lambda. We got lambda. Lambda is 3 hour or 1 over hour. So if I apply directly, I will get 1/3 of an hour or 20 minutes, right? An hour is 60 minutes, so 1/3 is 20 minutes. So that's the expectation, direct application of the expectation. What is the probability? Before I go to the next step, let me just try to get you into thinking of these in intuitive way, because sometimes you just need to think about things in an intuitive, common sense way. So if the average rate is 3 jobs per hour, right? Think of it. Somebody tells you that there are, or packets or jobs arrive at 3 jobs per hour. So on average, must be every third an hour we have something. We have a job. Third of an hour is 20 minutes. Right? Okay, what is the probability the next job is sent within 5 minutes? So here we are looking for the probability that x, or t, probability of t is less than, and it doesn't matter when we say less than or equal. For continuous, they are the same. So we're looking for the probability that t is less than 5 minutes. So our lambda was given to us as 3 hours, or yeah, 3 per hour, right? If I try to apply the formula here, which gives us the time less than or equal 5, I have to convert x. So lambda was given to us in hours, and x was given to us in minutes. So I cannot just simply plug these numbers. I have to convert either lambda and convert it into minutes, or convert the x here, or the t, depends on what kind of variable we use. So I need to convert it into hours. I have to convert one or the other. I cannot use 3 for lambda and 5 for x. I have to convert one or the other. So here we see that we converted the 5 minutes into 1 over 12 hours. So 5 minutes, 5 minutes out of 60 minutes. So that's 1 over 12. So rather than using 5 minutes, I'm going to use 1 over 12. And this is f of 112. So this is 1 over 1 minus e minus lambda x, right? Where did I get this from? I get it from here, the commutative distribution function. All right, so now I just need to substitute the numbers. So here, this is 3, this is 1 over 12, and I find the result. So this is, if I want to simplify it further, this is 1 over 1 over 4, and I use the calculator to find the result. So in this case, it's very easy to find the result using calculators. I don't need tables. I just need a calculator that has the value of E. So 0.25 negative so it's 0.22. Let's keep it just 2 decimals here. All right. So in the notes, it's 4 decimal precision, so 2212. In my calculator, it gives me 0.221199 and so on, right? So you stick to 1 precision. So dealing with exponential exponential distribution is often very easy. One important property of the exponential distribution is called the memory-less property. Right, so, and that needs a little bit of training. It's sometimes feels like it's counterintuitive. So let's say again I expand and say, well, given that the packet arrived in less than 5 minutes, what is the probability that the next packet also arrives in less than 5 minutes? So let's say you have this time scale here, and packets or jobs arrive randomly, right? It arrives at random times. So this random time between the events is governed by the exponential distribution. All right, so our first example said what is the probability that x here is less than 5 minutes. So we calculated that. Then it may come question like, what is the probability that the next packet after that arrives also in less than 5 minutes? So after the first packet arrives, the second packet also arrives in less than 5 minutes. So in that case, we'll use the same exact formula. Why? Because exponential distribution doesn't have a memory of the past. It's like a flipping coin in some sense. If I flip a coin 5 times, right? I say, what is the probability that I have 5 heads in a row? Well, every coin toss has no memory of what happened before. Every coin toss, the result is either head or tail, 50-50, right? Equal probability of each. In some sense, the exponential distribution also doesn't have a probability of the past. So it doesn't say, oh, last time I took a long time for the packet to arrive, so next time probably it will take less. No, it doesn't have memory. So every time we'll have, you will see here that this is the expression. What is the probability that t is greater than t plus x given that t is greater than t, right? And in this case, the probability is t is greater than x. And that is the mathematical way of saying there is no dependence on the past. Okay, so the next distribution here is gamma distribution. Gamma distribution represents multiple represents an experiment where we are looking for multiple events, one happen after another. Each event happens, or the time between the events is an exponential distribution. Okay. So, in other way, if I look at this example again, I say, all right, what is the probability that 5 packets arrive within 5 minutes? So this is the first packet arrives, then second packet arrive, third packet arrive, fourth packet arrive, and then fifth packet arrive. So each one, so instead of saying what's the probability that the next packet arrives within 5 minutes, which is one packet, now I can say what is the probability that we have 5 packets arrive in less than 5 minutes, or less than 10 minutes, or less than an hour. So we have multiple steps here, not just one, multiple steps. Or another example will be, what is the probability that I execute 4 programs or 5 programs in a row, and the total time that they take from the start to finish is 1 hour 20 minutes, right? So now we use geometric distribution. Geometric distribution looks like the exponential, but the exponential deals with one event, while the gamma distribution deals with multiple events. So the gamma distribution looks like this. We have lambda to the power of alpha. Alpha is the number of steps. Alpha is the number of events. Lambda is the same as before. This is the rate by which the events happen. Right? So because of this, this is the gamma function, and the gamma function is actually a form of a factorial. Because of this, it's not when we take the CDF, the CDF doesn't look nice formula. The CDF has this integration, and it's not easy to calculate, right? So gamma is a little bit more difficult to calculate with the calculator, and we probably need to use tables for it to calculate, right? If I simplify, as I said, gamma is just it it represents multiple events happening at the same time, where each step takes exponential amount of time. So if alpha here is 1, this is reduced to exponential, right? So if you calculate if alpha is 1, it's the same as the exponential. And if alpha is, or if lambda is half, this is a special case where we get the chi-square distribution. We're not gonna deal with chi-square here in this course, but it's another common, well-known distribution. All right. So let's see an example here where we are looking for compilation of a computer program consists of 3 blocks that are processed sequentially, one after another. Each block takes exponential time with the mean of 5 minutes independently of other blocks. Okay. So here, that's a clue of using a gamma. So we're looking for 3 blocks. Each one of them is executed one after another, right? The time for each block execution is random, but it follows exponential time with 5 minutes, with a mean of 5 minutes. right? And they are independent. So compute the expectation and variance of total compilation time. So we need the expectation and we need the variance. Actually, so what is the expectation? The expectation for the, if I just put the um, um, the numbers here on the side, right? For the exponential time, remember the expectation is 1 over lambda. For gamma, the expectation is gamma over lambda, or gamma multiplied by expectation of the exponential. So here, gamma in our case will be 3 because of 3 blocks. So gamma is 3. The expectation of exponential distribution, it was given to us 5 minutes. That's the mean. So that's for exponential, by the way. So what is the expectation for gamma? So this is alpha over lambda. This is 1 over lambda. So it's simply 3 multiplied by 5, or 15 minutes. Again, intuitively, if the time that each block will take on average is 5 minutes, so 3 blocks, it's 3 multiplied by 5, 15 minutes on average. Right? Okay, now what is the variance? So the variance here is alpha over lambda square lambda square is 1 over 5 minutes, by the way, right? So 1 over 5 square. So that's 3 multiplied by 25 minutes, or 75 minutes square. All right, and compute the probability for the entire program to be compiled in less than 12 minutes. So what we're looking for is the probability that the time will be less than 12 minutes. So here we need to find this value using alpha equal 3 and using lambda equal 1 over 5. All right, so in this case, we probably need to figure out if we can find it using tables, or we have to do it this way, where we have to solve the integration. Now, unfortunately, we don't have tables that solve this. So what we need to do is just in the notes we show you how to do the integration and get the result. But we have a way to approximate the gamma with Poisson, right? There are actually similarities between the two. Remember, Poisson is the number of events that happen within certain time, and I said that it has the events, the time between one event and the other is exponential. But if you have multiple events, right, the total, imagine the Poisson total time is the accumulation, or the addition of one time after another between the events. So we can find the gamma solution using Poisson. We just need to make some adjustments. And you will see this is another example where we can do approximations to find one solution from another, one solution for a distribution from another distribution. So here we have this relationship. I can replace the probability of t greater than or equal t with the probability of x less than alpha. The left side is the gamma. The right side is Poisson. Right? And just we need to take care of the sign here, because remember, in the discrete there is a difference between greater than and equal, while in continuous distributions there is no difference. So we have to be careful here. All right, so let's see. Poisson needs parameter mu. So how can we get mu? By multiplying lambda with t. Right? So lambda comes from the gamma distribution, and t is the total time that they asked us to do, right? And then we have these formulas here that the main purpose of these two lines is just to adjust the greater than or greater than and equal. So in our example, we need to find the probability of t less than 12. So we need to find this here. All right, so if I'm gonna write it down, I'm gonna write it down as p x greater than or equal alpha. So this is the probability of t less than 12 minutes is the same as the probability of x greater than or equal, and I have alpha here is 3. And I'm going to use mu equal lambda t. What is mu? What is lambda? Lambda is 1 over 5. And what is t? T is 12. So I'll get my mu here. And if I find the right tables, or if I solve it by substituting in the formula, I will get the same result as 0.4303. Now, if you try to go to the tables and try to find the solution, you will find hard time finding the solution, because mu here is not an integer, while all of our tables mu is an integer. So we want, in our table that we'll use in this course, you won't find it, you won't find the solution. But this is just an example in the notes. We can, in the assignments and the quizzes, there will be something that you can find in the table, right? So there will be no case where you will find a number that you cannot use the tables for. But just this is to illustrate that we can actually instead of integrating this formula here at the top, we can use the Poisson with the really simple substitution. All you need to do is find mu, which is lambda multiplied by t, right? And use these formulas. Make sure that you are using the right formulas, and make sure also that when you use tables, remember the tables, you won't find this x greater than or equal 3. What you will find is f of x, which is probability of x less than or equal small x. So in our case here, if I want to find x greater than or equal, probability of x greater than or equal 3, I have to find the probability that x, remember this is 1 minus x less than or equal to. Great, this is how it works. In our case, we are supposed to get 3 here, so we will substitute that by 1 minus f2. And this will be found in a table, right, using mu. All right, let's move on to the normal distribution. Normal distribution is also very, very common distribution. It actually represents a lot of natural phenomena. So one example, if I take any measurement, let's say measurement of a table, right? And if I ask 10 people to measure the table, each one of them will have a measuring tape. Now, it will be impossible for everybody to give me an exact measurement. The tapes probably will be different, slightly different. Everybody is going to read the number on the tables differently. So if you get all the numbers from all the people, you will find that the numbers are randomly distributed, and the distribution will be a normal distribution, right? So the normal distribution is famous for its shape, which is a bell shape, right? It's centered around mu, and it has a standard deviation. So now the mu and the standard deviation explain or describe the normal distribution, or the Gaussian, sometimes Gaussian called because it's the shape, right? So if it's tight like this means that the sigma, or the standard deviation, is small. If it's wide, means that the standard deviation is large, right? So the higher the number of the standard deviation, the wider the bell curve, and if the standard deviation is small, it will be tight, right? And this represents, as I said, errors in measurement. A class marks, normally, if everything is okay and there is no strange phenomena happening, the marks in a course will be distributed in a bell shape. So if I take the frequency, if I take the number of people who got from 50 to 55, and then the number of people who got from 55 to 65, and the number of, so if I calculate the number of people that got marks, I'll get a bell shape. And this happens all the time. And this is how I find if everything is normal or if there is something strange happening. If I see the curve of the marks is somewhere like here, means that maybe a lot of people got good marks, right? Um, Unnaturally good. Or if I see something like this, means that okay, so I have a probably skewed some, and neither one of these is a Gaussian, right? Neither one of this is normal distribution, so the normal distribution should be like this, right? So a normal distribution, as I said, describes a lot of phenomena, and also it is related to something called the central limit theorem. So the central limit theorem says that the sums and averages often, so if I take uh, the averages of many distributions, random variables from different distributions, their sum and average follows normal. And we'll talk about this later on. But the normal distribution has this function, sigma 1 over sigma multiplied by the square root of 2 pi exponential function of this. So it's a little bit ugly, and it's not easy to integrate so that we can find the CDF for it, right? So we rely on tables to calculate this. Also, as I said, the mean is mu and the variance is sigma square. So the standard deviation is sigma, as I said. It looks like this. So it's always centered around mu. If mu is 0, then it's centered around the x-axis, right? So because mu can take any number and sigma can take any number, there will be, we will have a hard time finding a table that will give us any probability with variable mu and variable sigma. So as we did with the uniform distribution, we need to standardize the distribution. So we need to make sure that mu is always 0 and sigma is always 1, so we can create one table, right? So we will call this the standard normal distribution. There are some notations that we'll use. So for the you'll see the phi in capital Phi here. This is the PDF, the top, and the CDF, the bottom, right? So this is what we will find um, in the tables. All right, so how do we find the standard? So if x is the regular normal distribution, the standard normal distribution is always or commonly given z, the notation z, right? So z, if I want to standardize any number, so I'll say z, which is representing our standard normal distribution, equal x, which is representing our regular normal distribution, normal variable, regular random variable that follows the normal distribution, if you want to say it correctly. So that's x minus mu divided by, was it sigma? Right. And So that once I find that, I can use tables and I can use these two formulas here to find the probability. And if in some cases I want to convert things back to the regular random variable, so I'll use x equal mu plus sigma z. Right. So let's take some exercises. So, and this usually by looking up tables. So probability of z less than or less than 1.35 equal f of 1.35, or this thing here, which is the symbol for the CDF, which is phi 1.35. If I look up the tables, and let's see what the tables look like. So if I look up the table and go to the normal, so the standard normal has z with negative numbers. These are the numbers that below 0 or above 0. So our random variable was 1.35, I believe. So 1.35, so this shows me only 1.3. But if I go further down, so this is 0, 0, 0, 1. So think of it as 1.31, 1.32, 1.33, and up to here. So that will be the probability of x less than 1.35, and it's 0.9115. Which is this number here. And if I want to go greater than, that's a standard, so it's 1 minus, so I'll get the other side, which is 0.0885. If I want the number between, or the probability between minus 0.77 to 1.35. So let's take a look at this one. So minus 0.077 and 1.35. I need the probability of this. Just to confirm again. Oh, it's 0.77. Okay, so it's not 0. Alright, so if I want to go and find these numbers in tables, so this is equivalent to the probability of z less than 0.35 minus probability of z less than minus 0.77. If I want to explain it in a diagram, right? So let's say this is here. Sigma is always standard 1, right? So I'm looking for the probability 1.35. And probability, let's say this is 0.77. So I am looking for the area in between. So the area in between, if I take probability of z less than 1.35, so this is what the CDF will give me, and also this is what the CDF will give me for probability z less than minus 0.77. So if I subtract these two values, I'll get this blue. All right, so let's find out. By the way, Well, this is the normal notation is equivalent to this. Let's go to the tables and find out these values. So 0.35 is 0.9115 as we said earlier. So let's look at the other one, which is negative 0.77. So here's negative 0.7, and if I go further, where is the table here, common? So this is 0.7 here, the top. So I'm looking at the third column from the right. That's 0.2206, right? So if I subtract the two values, 0.2206, and this was 0.9115, I believe. Let's double check, make sure that yeah. All right, so if I subtract the two, point 0.6909. All right, let's compare that with the result in the notes, make sure that didn't make any mistake. Yeah, 0.6909. Okay, so that's correct. All right. All right, so the second example here is a little bit interesting, where the difference here is that the probability was given to us. Um, or actually, yeah, not the probability was given, but what we were given is the regular random variable, and we want to find the standard random variable. All right, so let's take a look step by step. Suppose that the average household income in some country is 900 coins. Average means mu in this case, and the standard deviation is 200 coins, so sigma is 200. Assuming the normal distribution of incomes, compute the proportion of the middle class whose income is between 600 and 1200 coins. All right, so let's keep these numbers in mind. So we have mu is 900, sigma is 200, and we want to find the probability, which is the proportion of people who live or who has income between 600 and 1200 coins. Okay. So we will write that in our notes here. So we're looking for probability of x greater than 600 and less than 1200. And we are told that mu is 900 and sigma is 200. So if I try to go to the tables and find out the result, I won't be able to do that. Why? Because our mu is always 0 in the tables, and our sigma is always 1 in the tables. So I need to convert this to a standard. So I can convert that by saying, remember, z, the standard normal, is x minus mu divided by sigma. So I can say 600 minus mu, which is 900, divided by 200 and convert this into standard. So we're looking for these numbers. Okay, so 600 minus 900 is 300 divided by 200, that's minus 1.5. And 1200 minus 900, that's 300 as well, divided by 200, that's 1.5. So I'm looking for the solution to this. The number between z between 1.5 and minus 1.5. So the tables 1.5 here positive is 0.9332, and minus 1.5 is 0.668. So if I go back to my notes here, 0.9332 minus 0.0668, and if I use the calculator here just to subtract, 0.8664. So that's the proportion or the probability that people in that country having an income somewhere between 600 and 1200 coins. Alright, so that's the result here. So here in the second example, the government decides to offer tax relief to the poorest 3% of the households. Below what income will families receive tax relief? So here we're given actually the probability, and we need to figure out how many coins these people earn. So if the probability of x less than x, small x here, is 0.03, what is the actual income? So now let's take it step by step as we did before. Remember the 0.03. So the probability of x less than small x is 0.03. We don't know what x is, so that's the question. The question is, what is x? What is the number of coins? Right. All right, so again, I need to standardize this. So here we have z less than x minus mu divided by sigma. That's what I want to find. So let's find what is the probability or what is the number that corresponds to probability 0.03. So let's go to the table. Here actually it will be a little bit hard. So we're looking for these numbers here, and we're trying to find 0.03, which is 3%, right? So this is 0.0359. And if I go further down the line, I get closer to, this is the closest thing to 0.03, which corresponds to corresponds to z, right? Because this is a standard, corresponds to z equal minus 1.88. So here, if I go back, so this is point z, z less than minus 1.88 equal roughly 0.03, right? Let's double check. Minus 1.88, the column here 0.8, 0.08, and the row here is minus 1.8. So that's our value z. All right, and as we said before, z equal the regular normal minus mu divided by sigma. So I found z, I need to find x. Mu from the top is 900, and sigma is 200. So now I have to do this, x equal minus 1.88 multiplied by 200 plus 900. Let's see what x means here. So 200 multiplied by 1.88 negative, add 900. So the result is 524. So the 3% that are considered poor by this government, they earn 524 coins or less. And these will be given tax credit, 524 coins here. So they will be given tax relief. As I said earlier, there is a relationship between the normal distribution and the central limit theorem. And as I said, if you take any random variables from any distribution, right? If you take these random variables, if they are independent random variables with the same expectation, same standard deviation, their sum follows normal distribution, right? So as the equation here says, if we take the sum of x1, x2, x3, x4 up to n, if I assume that each one of these x's is an independent random variable, but it comes from any distribution as long as it has the same deviation and the same expectation, then S of n here is normally distributed, has or follows the normal distribution. And the larger the n is, the closer it is to a perfect normal distribution, right? So as n approaches 0, then we can say that the z of n here is a normal random variable, um, and or a standard normal random variable, and its relationship with the z is s of n minus n mu divided by sigma n square root of n, right? So let's see what that means. Um, let's say here is an example. A disk has free space of 330 megabytes. It is likely to be sufficient to store 300 independent files if each file has expected size of 1 megabyte with a standard deviation of 0.5 megabytes. So we want to find if these 300 files can fit in that free space. We don't know what the distribution of these files are. We don't know what the size is. Is the size follows exponential? Is the size follows uniform, normal, uniform? We don't know. We only know that the size of the files have a standard deviation of 0.5 megabytes and expected or mu is 1 meg. So we need to know if they fit. What is the probability that they will fit? So the probability that we'll have a sufficient space, right, is the probability that, first of all, S of n here is the sum of the size, the sum of the individual file sizes. We have 300 files. Each one of them is independent, the size independent of others. Each one of them has a mu of 1 meg and the standard deviation of, was it 0.5? 0.5. And we need to find out if the size Sn here is less than 330. We need to know if it fits. S of n is less than 330. All right? So, knowing that these are independent, we need to find the probability z, right? Less than something here. This is a regular normal, and this is a standard normal. So we need to convert to find this value from the tables. So to convert, we know that the probability here, so to convert from S of n to Z of n, we need to subtract 330 minus n mu divided by sigma square root of n. Right? So let's remove this for a second here. So 330 minus n, which is 300, multiplied by mu, which is 1, divided by sigma 0.5 square root 300. So if I'm going to do the calculations by myself here on the side, we'll find that let's take the new denominator first. So 300 square root That's 17.32 multiplied by 0.5. That's 866. So we are dividing 30 by 866, which is it's about 3, 4, 6. Right. So we need to find the probability here of Z less than 3.46. So if we go to the tables, 3.46 is somewhere here, 3.4, and 6, where we find 6, 6 in this column, which is the fourth from the right. So we're looking for 3.46, which is this column here, 0.997. Was it 3 nines? I think it was 3 nines. And then 7. This means that there is a high probability that all these files, the 300 files, will fit in the hard drive, right? Because the probability is very high. You will see a lot of examples like this, and actually the central limit theorem can be used to approximate a lot of things that we did before, other distributions, as long as the n is really large. So don't just run and use the normal distribution to approximate everything. N has to be significantly large for the normal to work. So you see here there are relationships to other distributions. The binomial, if you think about it, is the sum of independent Bernoulli variables, right? We looked at binomial as our first discrete probability distribution, and the result is of a binary experiment, either success or fail, success or fail. If you sum all the binomials, you will get the Bernoulli. If you sum all the Bernoulli, you get binomial. I reversed that, sorry. Right? So the Bernoulli is the result of binary outcome, either success or fail, and if you sum it, you get binomial. So every Bernoulli trial is considered an independent random variable that has the same mu and the same sigma. So if the number of Bernoulli variables is huge, right, 300, 400, you can actually use the normal distribution to solve the problem. Same thing with negative binomial. You can look at it as it's the sum of independent geometric variables. Gamma, you look at it as the sum of independent exponential variables, as we saw earlier. You'll have a packet arrives, then another packet arrives, and another packet arrives, and the gamma will find out what is the probability that the total time is less than this and that, or greater than this and that. So in fact, you'll see if the number of steps is high, you can approximate the gamma with normal. You cannot use it if the number of packets is, or the number of events is 4 or 5. But under this condition, n has to be really large, right? And the larger it is, the better the approximation. Right. So we saw before that we can approximate the binomial with other variables, with other probability distribution. Now we can see that we can, with actually Poisson, if you remember, now we can approximate it with normal if the probability is between 0.05 and 0.95. Remember previous approximation in a previous lecture, the probability has to be less than 0.05. It has to be very small, or it has to be very large, and I can flip it so I can look for the failures instead of the successes. Right? Here, if the probability can be somewhere greater than 0.5 and less than 0.95, I can use the normal to approximate the binomial. Right? And also, it has to be, n has to be large. So we'll see some examples in the exercises that actually um, we can approximate the binomial with normal. Now remember, the issue with binomial is it had the factorial. It has n choose x, and then we have p to the power x and p to the power n minus x. So these, when the exponential is large, we'll get really large numbers to deal with. So we need approximations, and we saw one way to approximate that, and this is another way to approximate. And you can find that you can convert the binomial and solve it using normal by calculating mu as np and sigma as the square root of np multiplied by 1 minus p, or q, npq. Okay, but there is one important thing to remember, and this is the same thing that we started this lecture with, is that when we deal, now we have a mix of continuous and discrete. Binomial is a discrete normal distribution, discrete probability distribution, while normal is continuous distribution. And for continuous distribution, px equal x is 0. So what if somebody says, well, give me the probability of x equal x here for binomial? I cannot just apply I cannot just go and approximate that with normal, because normal will always give me 0. So for this curve, if I try to find the probability of x equal x here, we'll get 0. So instead, I have to find the probability of a small range around this value. So instead of finding exactly x equal x, I have to find the probability of x, maybe x plus something s here, and x minus s, right? So I have to find s or epsilon or any other variable. So I have to find the range instead of just a single value, because a single value will give me 0. So that's what we will call the continuity correction here. So the correction is needed when we approximate discrete distribution by a continuous distribution. And the S that I mentioned is, in this course, we will assume that it's 0.5. So when we try to do approximation, we will just add 0.5 and subtract 0.5. So the range will be, if I am looking for x equal x for binomial, for example, and I want to use normal, I have to take the x, add plus 0.5 to it, and subtract, and so I have to go range 0.5 to the left and 0.5 to the right. Okay. And this is an example of using a binomial distribution, n equal to 100, p 0.2, mu is np, 40, and sigma is 5.657. So if I want to find the result using normal, then I have to, since I'm looking for the range less than 50, so I actually went a little bit less and subtracted 0.5. In your here there is a table that gives me all the corrections that I need. So if I need the exact x equal n, then I'll add n plus 5, n minus 5. If I need x greater than n, then I add 0.5 here in the normal. If I need less than or equal n, also add some corrections. So all of these, the corrections that I need to calculate the exact, or approximate binomial, or any one of those discrete random variables, that discrete distributions that I talked about. I can use these corrections if I want to approximate them with normal. Okay, so this concludes the probability module actually of the course, and next we'll talk about cryptography, right? Which will use some of the principles that we know about probability in cryptography, and they're related, of course. Okay. So with that being said, thank you for listening, and we'll talk in the next chapter.